All right, hey guys, today we're going to talk about simple harmonic motion, but the systems in which we're going to observe simple harmonic motion will be pendulums rather than the springs that we talked about last time. So, what we're going to deal with today is something called a simple pendulum. And a simple pendulum is just an object that is suspended from a light wire or a string. And a simple pendulum is going to operate like a simple harmonic oscillator when it is following or when is it under certain conditions. Right. So it's going to produce the arc of a circle as it moves around its anchor point, right? And we can see that in our diagram below. As we let go of a pendulum bob, it's going to swing back and forth along the arc of a circle, right? So we're going to make a little bit of a smiley face. And because of that, we can kind of define the displacement of the pendulum as the arc length that it has from its point of equilibrium. And that point of equilibrium, of course, will sit down when it is not in motion. It will just sit right here, and that will be its XEQ, right? And that, we can think about that as making an angle with the vertical, and the angle right there will be 0 degrees, right? And then when we move it to any other position, we can find an angle, and that angle will be some number of degrees from that original vertical position. Okay, so we've got our pendulum here again. Again, this is a nut on the end of a string, so the nut will function as our pendulum bob, and the string obviously is part of our pendulum system here, right? So if we bring it back in either direction and let it go, it will oscillate with oscillating motion, right? Back and forth it goes. Now, if we take and we hold it at any given position, we can make a free body diagram for the forces acting on the pendulum bob, the nut at the end of the string, what forces are acting on it, right? So let's think about all the way up at the top end of the arc here. Once this thing turns around and starts going back in the other direction. So once it reaches the top end of its arc, we're going to have a few forces working on our pendulum bob. Why don't you pause the video right now and think about what forces are acting on our pendulum bob, and what, if any, of those forces or components of forces are canceled out, and what is left over to provide our net force. Take a moment, pause, and we'll come back. All right. Okay, so if we take a look at this nut right here, we've got two forces that are acting on it. The force of gravity obviously is pulling it down, Fg, and we of course have the force of tension pulling up into the left direction, right? We got Ft. Now, a question you might be thinking to yourself is which one of these is larger than the other, right? And what we need to do is we need to look at the net force acting on our pendulum bob. So if I pull it back to this point, which direction is it going to accelerate in? It's going to accelerate in this direction, right? Along tangent to the arc of that circle that it's making through its pendulum motion, right? So we're going to have acceleration from this point down in that direction, right? Which means that our net force is in that same direction. So if I drew a little ghost line here to represent some component of one of these forces, that's what's left over to provide our net force, right? And obviously, the only force that can provide that component is the force of gravity. So I'm going to call this Fg. I'm going to call this Fg perpendicular because it is perpendicular to the length of that string. So if we use that string as a reference, it's perpendicular to the length of that string, right? This is opposite to what what system of reference we would have used on an inclined plane, where this force of gravity would have been the parallel component because it's parallel to that slope, right? But here, our reference really is the length of that string, or that's what I'm using as reference, and so it is perpendicular to the length of that string, right? So good, and that's what's gonna be left over. That's gonna provide our net force, right? So this will be our net force, and that is what is providing our acceleration, because the rest of the force of gravity, whatever's left over that's perpendicular to that perpendicular component, or what we could call the parallel component of gravity, Fg parallel, that component that's parallel to the length of the string, that's going to be equaled out, going to be balanced out by the force of tension from that string, right? And we know that because if I let this pendulum bob go from this position, it's not going to accelerate towards the string. It's not going to accelerate away from the string. It's only going to accelerate perpendicular to that string, right? So the forces in that parallel direction, the net forces are canceling out to become 0, right? So that's how pendulum bob works, and we can find this restoring force the net force is left over from the interaction between the force of gravity and the force of tension for any point along this pendulum bob's motion, right? Right here, the net force is going to be 0, right? Our force of tension will cancel out our force of gravity. But each point along will have a different orientation of our force of gravity, which isn't changing, and our force of tension, which will be changing throughout the pendulum bob's motion. But some component of that force of gravity will be left over, and that's what will be causing its acceleration as we move through the arc until we hit the bottom, where the acceleration will be 0, but the momentum and the velocity will carry it through that point of equilibrium back to the other side for the restoring forces to act again just in the opposite direction, pointing always towards the point of equilibrium. Okay, and that free body diagram we made with our actual pendulum, we can replicate over here in our drawing on this slide. And again, we can take our net force, what is providing our net force for our pendulum, and that is a component of gravity that is perpendicular to the length of that string, right? And we can describe that mathematically with mg, or our force of gravity, times sine of theta, as long as theta is that angle between the string and the vertical, right? And we could also describe that with a negative because, again, that's a restoring force, so it is going in the opposite direction of our displacement. And note that mg cosine theta, this parallel component of gravity, right, that is canceled out because that will equal our force of tension. So that goes away and doesn't affect our net force. And as I hinted at when we were looking at our pendulum bob, this is analogous to normal force and the components of weight on an inclined plane, right? So some component of force of gravity is going to be canceled out by normal force there. In this case, that component of gravity, the one that's now parallel to the force of tension, is going to be canceled out by that force of tension. But what is left over in both cases is some amount of force of gravity that's going to give us our net force for this system. But in this case, right, as the bob moves along that arc of the pendulum, the angle, that theta, is going to change as we get further away from that point of equilibrium or closer to that point of equilibrium. So let's think about deriving an expression for a period for a pendulum. And first thing to note is that pendulums operate a little bit differently than spring systems, right? In a spring system, we have a spring, and within a certain range, that spring, the force of that spring should follow Hooke's law, right? The same sort of thing can be said for a pendulum, but it works a little bit differently. A pendulum is going to follow essentially Hooke's law for this restoring force, that parallel component of the force of gravity that's producing our net force, but it will follow something approximating Hooke's law within a certain range. And that range is about 15 degrees of the pendulum's arc. So the maximum arc that we can get to is about 15 degrees away from that point of equilibrium. And within that range, there's something called the small angle approximation, which is, if you're interested, you can go into the slideshow and click on this link. It's got some explanation of how the small angle approximation is derived and what it means. And what this tells us is that the sine of an angle is approximately equal to that angle in radians, which means that our mg sine theta equals about mg theta. Again, if we're expressing theta in terms of radians. So this should be about equal to negative mg theta. And so we can approximate that force as about negative mg theta, approximately negative mg theta. And this can be really useful to simplify things, because then we can express, since we can express our restoring force in terms of theta, now we can go back and think about the arc length along a circle, right? So again, a pendulum is going to curve out a path that's the arc length around a circle. The circle that we can make, bringing that string all the way around its point, its axis of rotation, its point of connection to whatever it's connected to. And so that arc length we can represent with delta S. And remember that S is the radius of that circle times the angle, angle displacement around that circle gives us our delta S. And so we can, and since our radius is equal to our length of our pendulum bob, we can just substitute that in. So our arc length, S, equals S equals our length of the pendulum, length of the string connecting the pendulum, times theta, times that angle that we brought the string from its equilibrium position to another position. And so if we rephrase that, then we get our theta equals S over L. And we can substitute in that in for theta into our force equation, right? So that gives us force is approximately equal to negative mg over L times S. And if we compare that to Hooke's law, we find that this looks very similar, right? So again, we said that S is our arc length displacement, right? Which that is correlates with our displacement or x. And then now we have this term mgl that is approximately equal to k. Again, within that range of 15 degrees on either side of our point of equilibrium. And now, since we can, now we have an expression for K, and we can plug that in and insert it into our period for a spring. So remember that our period for a spring was equal to 2 pi times the square root of the mass of the weight on the end of the spring divided by K, the spring constant of that spring. And now if we substitute in for K, that mg over L, we can simplify this equation by canceling out those m's and then fixing that fraction within the radical, right? So our period for a pendulum, which we can express as T sub P. This is T being period, P for pendulum. So the period of a pendulum equals 2 pi times the square root of the length of that pendulum divided by G, the acceleration due to gravity. And just before we leave this slide, one reminder that we built this equation, the period for a pendulum, off of that period for a spring, right? And we did it under the assumption that the restoring force of the pendulum, that mg over L, is acting like Hooke's law, right? And remember, that only works when our angle is less than or equal to about 15 degrees, because that's the range in which we can use that small angle approximation. And so within that range, the combination, the net force provided by the force of tension and the force of gravity will approximate the restoring force of Hooke's law. But outside of that range, it no longer will operate in the same way. And so the further we get from that 15 degrees for our maximum angular displacement for our amplitude, this will act less and less like a spring system, will follow Hooke's law less and less. And so we will not be able to use our period for a pendulum equation if our pendulum swings further than that range right there. So now we have that period of the pendulum. We can notice that it's dependent exclusively on the length of that pendulum. And of course, the acceleration of the gravitational field in which it's placed, which for the most part, we're not going to, since most of the work we're going to do here is on Earth, we're not going to change that G very much, right? So it's really just L that's going to change in order to give us a different period of motion, a different period of the pendulum. So interestingly, the period and thus the frequency will not be dependent on anything else other than the length of the string, including the mass at the end of the pendulum. And obviously, the acceleration of the gravitational field will always be g, and that's why really all we care about is the length. That's the only variable that we can really change here on Earth. All right, guys, so as we found, we know that the period of a pendulum is equal to 2 pi times the square root of its length divided by the acceleration due to gravity. Which means that now we can compare a few different pendulums and predict how their periods will compare to one another, all right? So let's think about length, all right? So length is our variable here that will actually influence things. So if we've got two nuts, they're the exact same nut, they weigh the exact same amount. I'm not gonna show you that. But if we take and we set them both into simple harmonic motion as pendulums, then we will find that their periods will not sync up, right? So we're gonna try to get them to about the same angle, which is, not ideally not more than 15 degrees, and let them go. And you'll see that they fall out of phase pretty quickly, right? The two of them do not have the same period, so this one is going at a much slower rate, and then this one is going at a much higher rate, right? Up here, All right, cool. So, good. And again, the longer the length, the greater the period, so the more time we would expect it to take to complete one oscillation, right? So our longer pendulum, it makes sense that it is moving slower and takes a longer amount of time to complete one oscillation, whereas the shorter one should be moving faster and will take a shorter amount of time to complete a single oscillation. All right, so let's get rid of that guy and let's take a look at our next pendulum. So up next, we've got two pendulums of the same length. So these guys are going to be the same length. However, they have two different objects on the end. All right, so about the same length. Let's compare their masses. So we've got the nut that we were using originally, and that one has a mass of 0.0513 kilograms, so about 51.3 grams. And then this stopper on the end of a string, that one has a mass of about 0.0292 kilograms, or about 30-ish grams. All right, so the two of them have different masses. And since those masses are different, let's compare what effect, if any, that has on their period. Let's see if they match up. And again, mass is not incorporated in our period for a pendulum. So if we set these guys in motion at essentially the same angle, we see that they are in near perfect synchronicity with one another. Because again, they should have the exact same period as one another, since G is acting the same on both, and they both have approximately the same length. We'll see they start to get a little bit out of phase, because again, really our length is dependent on our center of mass, which the center of mass of the two of them is probably slightly different. Let's compare this with the two of them both moving, but let's set them at different amplitudes, all right? So we're gonna set the stopper a little bit further than the nut right here, okay? So the nut, we're just gonna have a tiny displacement, the stopper a much larger one, and we'll let them go. You'll see that actually, even though they have different amplitudes, the two of them have the same period again. Just during that period, they're moving over smaller or larger spaces. All right, so as we just saw, the period of a pendulum, and therefore its frequency, will not be dependent upon anything, including the mass at the end of the spring or the amplitude, really anything other than the length of that pendulum, with the exception, of course, if we happen to change our gravitational field, our acceleration due to gravity. Under most circumstances, this would be very difficult, a variable that would be very difficult for us to change. However, we can use a pendulum to determine what that acceleration due to gravity is. And historically, this is actually how we've gotten some of our early estimates of what the acceleration due to gravity, what that number is. So let's try that out with this problem. Keeping in mind, again, that the period of a pendulum equals 2 pi times the square root of the length of the pendulum divided by g. Let's figure out what the acceleration due to gravity is in a region where a simple pendulum having a length of 75 centimeters has a period of 1.7357 seconds. So we've got a length of 75 cm, and let's put that into meters since we like our acceleration to be in meters per second squared. So that's 0.75000 meters, and then we have a period of 1.7357 seconds. And so if we take a look at our period for a pendulum equation, our period of a pendulum equals 2 pi times the square root of L divided by G. And so our unknown here is G, right? So let's put everything in terms of our unknown. So let's first square both sides. So we end up with our period squared equals 4 is 2 squared times pi squared times L over G. If we square the square root, we end up with just L to the first power over G to the first power. And then let's multiply each side by G to get rid of that G in the denominator on the right side, and let's divide each side by the period of the pendulum squared to cancel that out over on the left side. And so we end up with the equation that looks like this: G equals 4 pi squared L divided by our period of the pendulum squared. And so if we plug in our values for those, 4 and pi squared are numbers. L is 0.7500 meters, and our period for pendulum is 1.7357 seconds. We're going to square that. And you'll notice that our units will end up with what we have in the end are meters in the numerator and then seconds squared in the denominator. So we'll end up with meters per second squared, which we like because that's generally what we communicate acceleration in. And our answer ends up being 9.8281 meters per second squared, which is, of course, very close to the 9.81 meters per second squared value that we generally use. So this is a little bit larger, which means maybe we're closer to the center of the Earth. So perhaps this area where where the acceleration due to gravity, where this pendulum was swung, and we found the acceleration due to gravity in this region was below sea level, perhaps closer to closer to the center of the Earth, or perhaps to the north of the South Pole, which is also closer to the center of the Earth than the equator. So that's where we can find G, and that's how historically, again, pendulums were used to find G in the past, our first values for G. So just in summation here, we've got pendulums. We can find the period for pendulum using this equation, right? And interestingly, the only variable that we can really adjust here is the length. It doesn't matter what mass is at the end of the pendulum. It doesn't matter what amplitude we give that pendulum, whether we start here or whether we start here or whether we start a little bit further away. The only thing that does matter is that we can't, if we think about that theta, that angle between the vertical and the maximum displacement, the amplitude of our pendulum, that has to be less than or equal to 15 degrees, just because that's the only region of a pendulum's arc where we can approximate the restoring force of a pendulum to the spring force of Hooke's law. All right, so that's where this holds up. All right, thank you guys for learning today. We will explore this more in class.